We already talked about detection and attribution. We will revisit it in this context of adaptation and mitigation after we run through these various issues of Earth system science in the context of mitigation and adaptation. So the first one, of course, is a time scale. We talked about mitigation, where we are trying to reduce the hazard itself, for example, is a longer term process with 30 years and beyond. So mitigation cannot influence outcome in the nearer term, except if you go on YouTube channel and look at my lectures on bending the curve. There are short-lived short-lived climate pollutants like methane, aerosols, black carbon, and so on, which actually can have immediate impact if we start to mitigate them. So that would have a great impact on warming as well as health and so on, for example by reducing ozone in the troposphere. Adaptation is immediate next few years. Adaptation to variability and current climate change happens immediately already it's happening in places like India or Bangladesh or many places in Africa, or even in the northern hemisphere in rich countries over Europe and North America. Next few decades, adapting to changing mean climate state would be needed, maybe longer for major infrastructure and policy. Spatial scale goes from global key countries because of influence on climate or on decision making. Global considering reach of particular, if considering reach of particular institution in terms of adaptation. Role of non-greenhouse gas drivers of climate change, for example land cover change, urban heat islands. Urbanization is projected to continue, and urban population is expected to continue, and urban energy demand is rather severe. So they have a clear impact on climate, as we will see. For mitigation, we will need full system comparison of different mitigation options, and for adaptation, we will need improved projections at local levels, local impacts, local change. The adaptation targets at local levels are going to be very critical. Role of non-climate anthropogenic drivers of change, impacts of changes in atmospheric composition on biophysiological processes, ecosystem disturbances, and so on. In the mitigation column, we have unintended consequences of mitigation actions, so we have to be aware of those. Full system comparison of different forcing agents. So one of the unintended consequences, at least temporarily, will be when we clean up the atmosphere of pollution and aerosols. Temporarily warming may go up, but then eventually it has to come down because of the emission reductions that go with it as well. For adaptation, more complete picture of changes in risk are needed. Role of interactions between impacts, role of non-anthropogenic drivers of change, role of observations and attribution of existing impacts, what is already happening, modeling issues and tools. So we will go through these step by step, and we won't see the details of these things in mitigation. More complete and robust picture of consequences of different mitigation options. This chapter is more focused on adaptation. Sets context, so non-anthropogenic drivers of change sets context. Feedbacks, emission scenarios, ingredient integrated assessment models, general circulation models, regional climate models, and so on. Focusing more on adaptation, we will require complete assessment of all changes from all causes. Adaptation is to change, not just climate change in isolation. Okay. Establishing whether perceived changes are real, and to avoid maladaptation, because this is something like a wicked problem where you don't get to experiment, let's see what happens if we do this and go back and try something else. Some of the changes we make will be permanent, and they require enormous amount of resources, so we have to desperately avoid maladaptation and the unintended consequences associated with those. Emission scenarios, not so relevant, need to know likely plausible future changes. So when we make emission scenarios, we have to be aware that locally, what do they mean? What are the phase spaces of scenarios we are creating? Initialized forecasts and natural forcing to account for natural variability. So the time scale of years to a decade or two for adaptation is going to make it very critical that we build general circulation models that are able to do those and do multi-decadal projections and near-time initialized forecasts. This is what we referred to before as societally relevant timescales. Okay, regional climate models will become important. Multi-decadal projections and near-term initialized forecasts for a local adaptation. For example, restoring vegetation in the Western Ghats, how to manage agriculture without increasing flood risks or emissions, or food security and water security over the Gangetic Plain, how to help Bangladesh deal with its sea level rise problems while the ocean is warming and cyclones are intensifying, and so on. Weather generators and statistical downscaling, we won't get into details, but these are often needed to make scenarios of what the adaptation issues will be. Okay. Detection and attribution. Detection is obviously about measuring a change with some robustness and confidence. So here it is showing warming essentially from the Industrial Revolution into the 21st century, and we have already warmed about 2 degrees Fahrenheit, 1.8 or so, and in the last couple of decades it has accelerated, and we have on top of that natural variability with these ups and downs, including El Niños, PDOs, North Atlantic Oscillation, and so on. And detection is that we have some confidence that this change is above and beyond natural variability, either related to why does this do that? Either related to solar forcing or volcanic forcing and so on, or some other cause, that it is human caused. How do we do that? Typically just data will not allow us to do that, so we rely on models which are able to reproduce the observed trend, and in those models we remove selectively volcanic forcing, solar forcing, and anthropogenic forcing, and look for natural variability in this green curve here, what is added by solar forcing and what is added by volcanic forcing, which is usually a cooling effect. And when you add all those three with the greenhouse gases, we get the human caused impact. So this difference is what we are attributing to human caused changes in greenhouse gases and so on. So attribution can be a change in the probability of events. For example, if there was a massive heat wave in Siberia in 2010, you can look at it as whether the probability of occurrence of the event changed, or the probability was consistent with natural variability, but the amplitude of the heat wave was amplified by climate change. So those are different questions for attribution. One has to be very careful. So you look at in 1900 and in today, let's say year 2010 or 2016 when this was published, average number of years between events here was, let's say, 50 years, so it's called a return period. Let's say of very, very heavy floods in a certain region. Here, heavy rain events in along the Gulf in mid-August, and now it has come down to 30 years. Okay, so risk of similar events, the odds have gone up by 40%. This is what climate change does. It loads the dice. So when you throw a die, it's supposed to give you a number with equal random probability. The randomness is such that each number has an equal probability of showing up if you throw the dice enough number of times. But climate change loads the dice, so it makes it more probable that some number begins to appear more than random. This is typical 3-day heavy rain total in inches. In 1900s it was just over 20, and now it has increased by about 10%. Similar attribution exercises are done in many places, as we will see. So to do that, we obviously need a consistent long time series of data to even detect the change, and then try to make attribution exercises. So you're again looking